Hi, Algebra 2. Today we want to take a look at solving polynomial equations. And we're going to take some of the things that we learned about solving quadratics and apply that to solving equations that have a degree higher than 2. And so the things that we're going to look at today, determining if a binomial is a factor of a polynomial, factoring by grouping, to use synthetic division, which we talked about last time, and to factor sum or difference of cubes. And this sounds like a lot of objectives, but all this goes together towards our main takeaway from today, which is to be able to solve polynomial equations. So one of the things we want to think about is when we were working on solving quadratics, one of the ways that we learned to solve was by factoring one side, having it solve for 0, factoring one side of the equation, and then using the zero product property. If I have two factors that multiply to 0, then at least one of those factors has to be equal to 0. And that holds true if I have 3 or 4 or however many factors. If they multiply to 0, I can use the zero product property. So let's remind ourselves of what this looked like. So asked to solve the quadratic equation x squared plus 3x minus 10 equals 0. And so we can factor the left-hand side. Two numbers that multiply to 10, they have opposite signs because it's negative 10, and those same two numbers subtract to make 3. Well, 5 and 2 are going to be those numbers. And it's positive 3x, so the bigger number gets the plus sign. X plus 5, x minus 2 equals 0. So here's where the zero product property comes in. I take each of those factors and set it individually equal to 0 and then solve. I want to know, so what value of x makes x plus 5 equal 0? And what value of x makes x minus 2 equal 0? So I get x equals negative 5 and x equals 2. So I want to point out that you notice that because x plus 5 was a factor, negative 5 was a root of the equation. X plus 5 equals 0. When we solved it, x equals negative 5. And this is known as the factor theorem. We're going to use this as we move on through the remainder of the unit. The thing we want to keep in mind is for any polynomial, x minus a is a factor of that polynomial if and only if the polynomial value is 0 when we substitute a in. Another way to think about that is a is the x-intercept. So we want to think about this, is x plus 4, a factor of this polynomial, 2x squared plus 8x to the third plus 2x plus 8. So how would we know? We're going to go ahead and we're going to test it using synthetic division. So we recall that we have x minus h, right? So if I have x plus 4, that tells me h is negative 4. So I'm going to put that in my box. And then I'm going to go and take the coefficients of my polynomial. So this is x to the fourth, 2x to the fourth, 8x to the third. Notice there is no x squared term, so I'm going to fill that in with a 0. This is super important, otherwise we won't get the result that we need. 2x, 8. All right, so remember how synthetic division worked. I'm going to bring my 2 directly down. I'm going to take the negative 4 and multiply times the 2, and that product is going to go here. Negative 4 times 2 is negative 8. And then I'm going to add going down. 8 and negative 8 gives me 0. Repeat the process. Negative 4 times 0 is 0. Add going down. 0 plus 0 is 0. Negative 4 times 0, 0. Add going down. 2 plus 0 gives me 2. And then negative 4 times 2, negative 8. And this is my remainder. So if my remainder equals 0, then that tells me that this is in fact a factor of this polynomial. So this is how we do this. If we're asked to determine a factor, we use synthetic division. We're looking for a remainder of 0. So you could go ahead and try one on your own. You can pause the video here and use the same process. So is x plus 2 a factor of this polynomial? And what you learn when you did this is we ended up with a remainder of 25. Okay. 25 is not equal to 0, so that tells me this is not a factor. Now, if we were to go ahead and try and factor this because it's a quadratic, we would have reached the same conclusion. There is no pair of factors of positive 20 that adds up to negative 2. So no, x plus 2 is not a factor, and the remainder is 25. So a little bit later on, we'll learn about something called the rational root theorem, which is another way that we could have examined that polynomial and known that negative 2 is not a root. Every rational root of that polynomial could be written in the form p over q, where p is a factor of the constant term, in this case 5, and q is a factor of the leading coefficient, which was 4. So we would take all the factors of 5 and 4 and write them as ratios, and we would have found that we would not get an integer. So a couple more tactics. One of them is factoring by grouping, and the other is factoring the sum or difference of cubes. So factoring by grouping, you may recall this from Algebra 1. So we're looking at this polynomial, x to the third plus 3x squared minus 4x minus 12. And we're looking to see if each group of two terms has a GCF. So we'll group them up like this, x plus 3x squared, and then the other group is negative 4x minus 12. I can see that in the first grouping, I can take out two copies of x. So x squared is my GCF, the remaining polynomial factor, x plus 3. Then when I go to find a GCF the second time, I'm going to use this to guide me. If I do this right, these factors, x plus 3, will be the same in both cases. So I can see that I need to take out a negative 4. So the x squared and the negative 4, my two GCFs, those become two terms of one of the factors. And then my repeated binomial is my other factor. So x plus 3 times x squared minus 4. You may recognize x squared minus 4 is the difference of squares. We can factor further. X plus 3 times x plus 2 times x minus 2. So you may have noticed that the polynomial was third degree and that there were three roots, three factors, right? And that seems like such a crazy coincidence. Like, I wonder if it's like that all the time. And it turns out that it is. Okay? The number of roots of the polynomial will equal the degree of the polynomial. The graph of the polynomial is also going to have one fewer turning point than the degree, and we'll firm those things up as we move on through the unit. So let's take what we just learned and use that to go ahead and solve a polynomial equation. You can go ahead and give this one a try. Pause the video here if you like, and then come back and check your answer. So you may notice here that I used the exact same polynomial. All I did was write it as an equation. X to the third plus 3x squared minus 4x minus 12 equals 0. So we go through and we use factoring by grouping. X squared times x plus 3, negative 4 times x plus 3. X squared minus 4, x plus 3 equals 0. So x minus 2 and x plus 2, that's how this factors, difference of squares, times x plus 3. So I have these three factors, x minus 2, x plus 2, x plus 3 equals 0. So I solve each one of those individually. And I get x equals 2, x equals negative 2, x equals negative 3 for my solution. The last thing we want to look at is factoring the sum or difference of two cubes. So if I have two perfect cubes added together, a to the third plus b to the third, it factors this way. A plus b times a squared minus ab plus b squared. If I have a difference, I go a minus b and then a plus ab plus b squared. So if you're looking at these, here in the binomial that's degree 1, you have the same sign. Here, you have the opposite sign. So the sum of cubes, I want a squared minus ab. Difference of cubes, I want a squared plus ab. And then the last one is always positive. So let's look at an example. If we had x to the third plus 8. So x to the third is x raised to the third power. 8 is 2 raised to the third power. How do I know that's 2 to the third? Right? So you remember back in Algebra 1, you probably memorized the first maybe dozen perfect squares. You could run around going 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, and so forth. And eventually you'll do the same thing with perfect cubes. You'll recognize 8's a perfect cube, 27 is a perfect cube, 64 is a perfect cube, 125 is a perfect cube. The reason why we want to write it like this is so that we can now fit our pattern. So a plus b, so x plus 2 is one of our factors. And then I'm going to have x squared minus these two things multiplied together, 2x, and then plus this one squared. Okay. So when we have sum or difference of two cubes, we can factor it automatically using this pattern. So here's our big takeaway. If we can factor the polynomial, then we can solve the polynomial. Right? If we can set it equal to 0 and get one side in its factored form, we can use the zero product property. So how can we do that? Well, if we're given one factor, we can use synthetic division to factor it the rest of the way. Factor by grouping if that works. Sum or difference of cubes if that applies. Sometimes we're given a factor to test for, and we can use synthetic division. Sometimes we have to test our own factors, and we'll find out more about those as we move on through the remainder of the unit.